the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcome.
Hello, my name is Roy Simpson, professor of mathematics at Cosumnes River College in Sacramento, California. This video is for linear algebra students who are currently going through maybe some matrix equations stuff, and they've just learned about matrix equations, and they've previously learned about vector equations and systems of equations. This theorem, that is the focus of this video, is going to tie together all the solutions of all of those structures. Now, one thing you should note is there are some theorems, actually quite a few theorems in mathematics, that are somewhat obvious, like you kind of knew this already. So I'm just formalizing this with an actual theorem, but most students already knew it by the time they get to this point. So you probably knew it as well, but let's formalize it. The solution set for a matrix equation is the same as the associated vector equation. This in turn is the same as the solution set for the underlying system of linear equations. If you've been following my videos in the order that I've been producing them, then you totally know that a system of linear equations can be rewritten as a vector equation, which can be rewritten as a matrix equation. So this theorem should totally make sense to you. You will often be free to choose which form to use, but the matrix equation will be the best most of the time. Now, I actually wanted to just prove this in this video, that's all. And this proof is going to be a little bit of a long proof. I don't mean for it to be, but it just is that way. We're going to go ahead and start with the matrix. Let AX equals B, that matrix equation right there, have the solution some vector C. That is, when you plug that vector C in, it solves that equation. Or in other words, A times C is equal to B. Now we're going to use the convention that A sub 1, A sub 2, all the way through A sub n are the column vectors that represent A. And we know by matrix vector multiplication that the elements in the vector C are just going to be the weights of the linear combination of the column vectors of A. So if C is a solution to that matrix equation AX equals B, then C satisfies this linear combination of the column vectors of A, or that is, C satisfies this following equation. So what did we just prove? We proved if C is a solution to the matrix equation, then C is a solution to the related vector equation. Moreover, I'm going to actually label my equations, just a couple of them, because I'm going to need them. So 1 implies the following. Now that looks pretty messy, but all I'm basically saying here is that the vector, the column vector A sub 1, has m elements, because I'm assuming that A is an m by n matrix. And so what I'm doing here is labeling appropriately. This element right here is from the first row of the matrix A and the first column of the matrix A. This entry right here is from the second row but first column, and so on and so forth until you get to the mth row and the first column of A. It's the first column of A. It's just first, second, third, fourth, all the way to the mth row of that. Likewise, the second column of A, we have the entry in the first row, second column, the entry in the second row, second column, then we'll have the third row, second column, all the way down to the mth row, second column. And this process continues until you get down to the nth column vector of A. And if you take a look at that nth column vector, its first entry is from the first row of A but the nth column, from the second row of A but the nth column, and so on and so forth until you get to the mth row of A and the nth column. That's just a nice way to label those elements. Now, if you distribute the scalars into those vectors and you equate rows, you get the following. And that is a system of linear equations. And basically what this means is those constants C1 through Cn make all of these equations true. Hence, C1 through Cn, the point, C1, C2, C3 all the way to Cn, is a solution of the following linear system. And there we have it. Now, that's not the entire proof, to be honest with you. That's only one part of the proof, because all we've shown really is, what if I have a solution of this matrix equation? Well, now I've proven that that solution is the same solution to the related vector equation and the related system of linear equations. But now I have to go to each of the remaining two, the vector equation and the system of linear equations, and say, well, what if I have a solution to this, for example, vector equation? Is it a solution to the matrix equation and the system of equations? Yes, it is. And then I have to do the same thing for the system of equations. But I'm way too lazy, and I know that you've probably kind of started staring off into space at this point, but this is the major kind of thrust of how the proof works. It's 1/3 of the proof. It's not the entire proof, but it is how the proof works. There's no real point of me to go through the entire thing. I'll say proof 1/3 of the way through. All right, so I will not call that proof complete, because technically it's not, but it's not one that I would expect students to go through and just do completely through, because it is kind of mind-numbing. All right, that's all I want to do in this video. I hope it was somewhat helpful. It's just introducing a theorem and giving a partial proof. All right, I will hopefully see you in another video. Hopefully I don't bore you too much. Have a great day. Be a great human.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcomes obstacles getting in our way. Cause affects more than we can sometimes see. Things for what they are and work together until you feel at peace. Just listen close. Don't talk too much that isn't kosher. You may really hurt inside. It doesn't justify you to speak too loud and cry.